So we're going to do part 2 of section 6.7, and I just want to go over a couple other questions that come up in this section. The first one is this. Let's say a train or an engine that you attach to a train pulls that train 140 miles. Then a second engine, whose average rate is 5 miles per hour faster than the first one, takes over and pulls the train 200 miles. The total time required for both engines is 9 hours. So find the average rate for each engine. So this is what we've got. An engine pulls a train, and let's see here, 140 miles. And a second engine that's 5 miles per hour faster. Pulls the train 200 miles. Now the total time required for both engines is 9 hours. And so what we want is find the average rate for each train. So again, we want to break this down into what we know and what we don't know. So what is it that we know? Well, we know this. Engine 1 goes 140 miles. Engine 2 goes 200 miles. Now we do know something about the rate for engine 2. We do know it's 5 miles per hour faster than engine 1. So we also know that the total time is 9 hours. So what is it that we don't know? Well, what's unknown, and what they're asking us from the beginning, well, first off, the average rate of travel, or the speed of engine 1 and engine 2. Let me go back here and look at my E. All this rate will be consistent. And by rate, we do mean average rate. So we have the rate for engine 1 and the rate for engine 2. Now, we actually know something about engine 2, though. We know it's 5 miles per hour faster than engine 1. So what that tells us is if we know engine 1, we'll automatically know engine 2. So engine 1 seems to be pretty critical. Now, we don't know the time for each engine. Like, how long was engine 1 pulling for? Same for engine 2. Now, we do have a total time, 9 hours. But I'm going to argue the time isn't really as unknown as we think. There's something that brings all this together. Remember from these equations, we have an equation for motion that says time is the distance divided by the rate. So let's say we know the rate for engine 1. Well, as soon as we know the rate for engine 1, we know the distance is 140. So we take the distance divided by that rate, and we'll get the time. So the time depends on, again, knowing the rate for engine 1. Now for engine 2, if we know the rate for engine 1, because engine 2 is 5 miles per hour faster, we automatically know the rate for engine 2. And if we know the rate for engine 2, again, figuring that out from engine 1, then the rate for engine 2 will be divided into the distance for engine 2. That'll give us the time for engine 2. So everything ultimately is depending on knowing the rate for engine 1. If we know the rate from engine 1, we'll get the time for engine 1. If we know the rate for engine 1, we automatically know the rate for engine 2. And then from the rate from engine 2, we get the time for engine 2. So the rate for engine 1 is what we're all depending on. This is what we're going to make as our unknown variable, or unknown number, our variable. So we have a rate for engine 1. Now that means because engine 2 is 5 miles per hour faster, this will be our rate for engine 2. And we're going to make this observation then. The time for engine 1 will be the distance of engine 1, to be 140, divided by the rate for engine 1. And then the time for engine 2 will be the distance for engine 2 divided by its rate, x plus 5. So now with these expressions sorted out, let's come up with an equation we can solve. So the key that brings this together is that the total time was 9 hours. Now the time is going to be the time from engine 1 and then the time from engine 2, because engine 1 pulls for a bit, they switch engines, and then engine 2 takes over, and that gives us the full 9 hours. Now we have an expression for engine 1 time. It's 140 divided by x. And we have an expression for engine 2 time, 200 x plus 5. So we want to solve this equation. All right. So well, let's multiply through by common denominator. So let's take a look at these two denominators. And the reason we're going to do this, when we solve these equations, we want to eliminate denominators. It just makes life easier. So we have a denominator x, and then x plus 5. Now these don't factor into anything, so we just have x and x plus 5. But we do want to make these factorizations, however simple they may be, we want to make them the same. This one's missing an x plus 5. And this one is missing a times x. So now the factorizations are the same. We'll take this, we'll multiply through. It's going to cancel our denominators. So we'll distribute this. And so what we'll get So let's look for some cancellations. Again, we want to get rid of these denominators. Now here, the x's will cancel, excuse me. And here the x plus 5s will cancel. So this will give us x plus 5 times 140 plus x times 200. And this is going to be, we still got a 9, we'll distribute this x in like that. So it's going to give us 9 times x squared plus 5. So now we'll distribute the 140. And we'll distribute the 9. So we get 140x. And let's see here, 140 times 5, 500 plus 200, 700 plus 200x, 9x squared plus 45. So let's gather some like terms. Let's see here, we'll have 340x plus 700 equals 9x squared plus 45. And if we subtract, say, 340, 340x. The last thing to do, I'm going to put this so it's equal to 0. Then I'm going to use a quadratic formula on it. Oh, I'm sorry, this has an x. I forgot the x here. It's 45x. Woo. So let me take a look at this. We'll still subtract the 700. So don't forget, there's actually an x on this 45. Sorry about that, I missed it. Well, continuing on. 0, 9x squared, minus 340 plus 45x, minus 295x, plus 700. All right, so the numbers on this are going to get big. So let me double check here. Okay, that looks good. Now, we want to think of this in terms of, excuse me, a quadratic equation. So what that's going to mean, A equals 9, B is negative 295, C equals 700. So now we use the quadratic formula. Now the quadratic formula is negative b plus or minus the square root of b squared minus 4ac divided by 2a. So we're just going to take what we have here, substitute it. So negative 295. We're going to take the opposite. Negative 295. That's our b. There's the negative for the b. Plus or minus negative 295 squared minus 4 times 9 times 700 divided by 2a, or 2 times 9 in this case. The numbers are going to get a bit big. This is what we're going to have. Well, negative and negative is positive. Here we go. So if we square 295, or negative 295, what we'll get we'll get 8,725. And then let's see here. Let me run that number through real quick. I didn't write it down. Let's see. So we get 25,200 divided by 2 times 9, which is 18. Now, if we do the subtraction, oh, we had a negative in here. This is a negative 700. Forgetting my numbers. This was a negative 700. So the C should be negative 700, not positive 700. So that makes this a plus. So negative and negative is going to become positive. And so what that's going to give us is that. So don't forget the 700, C should be negative 700. That wasn't good. That should be our C. And so that's going to make this negative 700. Negative and negative is going to become a positive. And that's why we're adding these two numbers to get that. So if we take the square root of this, what we're going to get let's see, we'll get 335 divided by 18. And again, this is going to break down into, well, two scenarios. Minus version, we have the plus. Now, if we do the minus, let's see here. Well, we're going to get a negative number. And what we're looking for we want a positive number. Our rate is a distance over time, and distance is a positive number, and so is time. So we want this to come out to be positive. So far, it's not working. Let's try this one. 295 plus 335, 630. Well, that's positive. That's a good sign. And we get 35. So that seems to be a pretty good, reasonable answer. Now that's just x. We just solved for x. And if you recall, x is engine 1. It's the rate for engine 1. So we have x is 35, or 35 miles per hour. And then for engine 2, which is 5 miles per hour faster, that'll be 40 miles per hour. So that's the train problem. Let's take a look at one more, one involving work. So let's say you got this. You have to leave for campus in half an hour, or you'll be late. Unfortunately, you are snowed in. Now, you can shovel the driveway in 45 minutes. And your brother, who happens to be there, they can do it in 36. So if you shovel together, will you be able to leave for class in time? Or put another way, how long is this going to take, and can you do it in under 30 minutes? Can you do this under 30 minutes? Well, let's take a look at what we know and what we don't know. Now again, we're going to use an idea called the idea of a job, and we'll get to this in a little bit. So what we have first off is, what do we know? Well, we know for you to shovel the driveway, it takes you 45 minutes. And we're going to use a special ratio. It's task per time. And for you, it's one job. In this case, the job is shoveling the driveway. You can do it in 45 minutes. So we're going to put it like this. Now your brother is one job, 36 minutes. And you want to do this under 30. As a very minimum, you got to leave in the next 30 minutes or you won't make it to campus on time. So that's what we know. What is it that we not know? Well, we certainly don't know the rate of you finishing the job together. Don't know that. We also don't know something else. And this is the big question. How long is this going to take you to do this? Again, working together. You know how long it'll take you individually. It'll take 45 minutes. But what about the time for you doing this together? Now, again, I'm going to make an argument here. The key thing is the time working together. Because the rate, well, we have the one job, whether it's you doing it, your brother does it, or you do it together. You're just trying to accomplish the one job. So that part we know. What we don't know is the time it's going to take for you to get that one job done. So if we know the time, then the rate is just the job over the time. So we don't really, the rate, we know the rate as long as we know the time. So this will be our unknown. And so this is what we're going to need to do. I want to talk about this whole ratio thing a little bit. This is a special tool we can use. Now let's say there's a job that you can do in 10 minutes. Now, if you can do this job in 10 minutes, what this means is, well, let's say you have 20 minutes available. So to find out if you can do one job per 10 minutes, you've got 20 minutes to work, how much can you get done? We answer that question by multiplying. And so what we're going to get is 20 times 1 is 20. And you can put your invisible 1 here because we're multiplying fractions. So we'll make this an improper fraction by dividing by 1, which of course dividing by 1 doesn't change anything. But it does let us use our fraction multiplication. 10 times 1 is 10. And 20 divided by 10 is 2. And this kind of makes sense. If it takes you 10 minutes to get the job done, you've got 20 minutes. Well, you could do 2 of these jobs. Like, let's say you're making something on a production line, and well, it takes you 10 minutes to do it, but you've got 20 available. You can do the job twice. You can produce 2 of these things. Same thing if you have 30 minutes. If you have 30 minutes available, again, we'll put that over 1, multiply across. We'll just worry about the numbers here. 30 over 10. That's 3. So if it takes 10 minutes to do the job and you've got 30 minutes, you can do the job 3 times. Now, let's say you only have 5 minutes. Again, put it over 1. Multiply across. 1 times 5 is 5, 10 times 1 is 10. Reduce this down, divide top and bottom by 5. What you're going to get is 1/2. So this sort of makes sense. This little trick is kind of a helpful thing, because you have 10 minutes to do the job, and you only have half that amount of time available. You're going to get half the job done. So we're going to use this approach to solving this problem. Excuse me. Now, what's going to happen here is, in this case, we're going to have contributions from both of you, you and your brother. Now, you're going to work together for X amount of time. So that means for you, your contribution is going to be this. Now, you can do 1 job in 45 minutes. Now, you and your brother working together, you're going to do this for X amount of minutes. So how much of a job, or how many jobs, or what fraction of the job are you going to get done if you're only working X amount of minutes? Well, we take the amount of minutes like we did before, multiply it to that. So X. And again, put it over 1 so we can do our fraction multiplication. 1 times X is X. 45 times 1 is 45. So this is your contribution. And what about your brother? Excuse me. Well, for your brother, what you're going to have is 1 job in 36 minutes. Now, he's going to have, again, X amount of time to work on this. So how much of the job is he going to get done? Well, again, we take this ratio, we multiply by the time available. So 1 times X is X. 36 times 1 is 36. So with these expressions, we've got to come up with an equation. So what's going to happen is you're giving some kind of contribution. Your brother is giving some kind of contribution. And those brought together will complete the job. You'll get 1 job. So there's your part. There's your brother's. And when you put your efforts together, your contributions will add up to 1. Now, how much of the job are you going to get done? Well, we saw it. If you did this for X amount of minutes, you'll contribute X over 45. And if your brother works for the same amount of time, he'll contribute X over 36. And there you go. So now we just have to solve this equation. So again, we can come up with a common factor here. There's a real easy way to do this. I'm going to kind of expedite it because I'm running out of time. Let's multiply through. Well, yeah, we can do this. We could multiply through by 45 times 36. And that'll just make all those denominators cancel. Now let's be consistent though. Let's break it down how we have been. So I'll take the time, hopefully we'll make it. So 45, 3 times 3 times 5, 36. 2 times 2 times 3 times 3. So we want to make these factorizations match up. So this one definitely needs a times 5. And this one, it needs the times 2's. Let's take a look at this. 2 2's, 2 2's, 3 3's, 3 3's, a 5 and a 5. Okay, this works. So what are we going to get? And we'll get the same thing. So we've got 36 times 5. Is that 150, 180? Double check that here. 45 times 4. Yeah, 180. So we're going to multiply through by 180. Now you could do 45 times 6, and these will cancel. You'll get a 36, a 45, and the 45 times 36, but I'm being consistent. And 180. This is going to be X over 45. I'll distribute this. And I'll just be 180. So 45 goes in the 180 4 times. 36 goes in the 180 5 times. So what we're going to get, 4x plus 5x is 180. Or 9x is 180, divide by 9. And again, we're looking for minutes here. So how many minutes is this going to take? We're going to get x equals 20. So working together is going to take 20 minutes to get this done. And that's good news because you've got to get out of here in 30 minutes. So there you go. Now, if you have any questions, let me know, and good luck.